Okay, so our presentation today is going to be all about the Kalman filter with Ralph. Ralph, take it away.
Hi, the mic's working. Cool. Right, thanks, Osman. Okay, well, thanks for coming. So, as anticipated, tonight is the Kalman filter talk. If you came for the basket weaving demonstration, you're in the wrong place.
That's a muse right down the hall.
Right, that's unmute now. So, is my mouse working? As usual, there's a mouse problem. So, to get started, I thought I would talk about, very quickly, who was Kalman? Where did it get its name? It was invented, or named the Kalman filter because it was invented by a fellow called Kalman, born in the 1930s, and he died a few years ago. Educated at MIT, got his PhD in Columbia, published over 50 papers in his career. He's an academic primarily. Early career work was at IBM. Then he joined the Research Institute for Advanced Studies, RIAS, and while he was there in 1960 published his paper on the Kalman filter. Then went on to Stanford and spent most of his career as a professor at University of Florida. He's by some considered the co-inventor of the Kalman filter. Obviously there were people that came before him. Significantly, Norbert Wiener did a lot of very early work in signal processing and was the first person to publish how to denoise a signal. But Wiener's work and algorithms were very numerically complicated, very hard to implement, so they never became very popular. Kalman picked up on the ideas and ended up developing with some of these other people the Kalman filter, what we know as the Kalman filter today. The first credited use of the Kalman filter was by Stanley Schmidt, who was working at NASA in the 60s on the Apollo spacecraft navigation. He was struggling with some issues, had a meeting with Kalman. Kalman told him all about this amazing paper he just published, and NASA and those guys thought, well, this sounds like just what we want. They took it, ran with it, and helped put men on the moon by the end of the decade. Kalman, as well as the Kalman filter, his whole career was around control systems theory. He invented what we call today the state space model for system dynamics. No surprise, you'll find the Kalman filter uses state space representations. And he also contributed significantly to modern control theory, controllability, observability, optimal control. So a real pioneer in control theory systems. So, on to what is a Kalman filter? So I'll just let you read that, and once you understand, I'm pretty sure everybody will understand that, and then we can get into the real details. So, okay, probably not many understand what's going on there. By the end of tonight, I hope you will understand what's going on there. So, definitely a Kalman filter is a recursive estimator of the state of a dynamic system given a model and measurements of the system. And the measurements and system may be subject to noise, but if the model is linear and the process and measurement noise are Gaussian, then the Kalman filter is the best you're going to get. Okay, so what do we need to explain there? Recursive. Recursive just means it's a loopy algorithm. We take the output from one step, we feed it back into the next step. So it's an iterative process. It's very efficient because we just need the last output and the inputs to process the next iteration. Some of the other algorithms, like the Wiener filter, you needed the whole history of all of your data every time you iterated through, so it was very inefficient. Estimator, we see the word noise in there. Noise means random, random means statistics, statistics means statisticians, and we all know statisticians won't give you a precise answer. They're only going to give you an estimate of something. So because the Kalman filter is a stochastic algorithm that works with statistics, it's called an estimator. But with that, as well as giving you this estimate of the answer, it also tells you about the certainty or the amount of unknownness of the answer. We'll be talking a lot about that. So the state of a dynamic system, that's for us, that's our robot. That's the real physical world object that we're trying to understand, trying to get some information about. State of a system, okay, state has some precise mathematical definitions, but for us, we can just think about it's a list of the parameters that we're interested in about our robot. So it could be what's its x position, what's its y position, what's its heading, its velocities. It's just a list of parameters that we're interested in. We call it a state. So for tonight, we're saying it's called a state vector. So we have a loopy iterative algorithm that gives us estimates of stuff we want to know about our robot, given that we have a model and measurements of the system. So model doesn't mean we need a little 3D printed model of our robot to go along with it to make it work. Model is a mathematical model that we need to create that basically simulates the robot dynamics. Now that sounds pretty complicated, but it turns out in the sense of the Kalman filter, for most of what we would want to do with robot, the model turns out to be quite simple. We're going to go through a little bit of that as we go forward. I think everybody understands what measurements of the system means. So the filter, it's trying to give us an estimate of stuff about a real physical system. System and measurements may be something, no maybe about it, it will be noisy. The world is a noisy place, your sensors are noisy, we have to deal with noise, and just as well because that's exactly what the Kalman filter is designed to handle. So given all of that, if our model is linear, we can do a whole series of talks on what linear modeling is all about, but it just means it's a linear approximation. It's a very simplified version of the model of the physics. The simulation is not very detailed. It can be represented by a set of simple linear algebra equations. And if we can do that, and our noise is Gaussian. Gaussian describes how we might characterize a type of noise. We're going to be talking a lot about Gaussian noise, but it just puts some constraints on the noise and the estimate that we're going to be using. And if we meet those criteria, then the Kalman filter is guaranteed to be the best optional, or the best algorithm you could create to create an estimate of the state of a dynamic system. If you don't violate those constraints, no other algorithm can beat it. It's mathematically proven to give you the least possible error. In the long run, I mean, it's constantly you're iterating, you're getting updated states at each step, and the aggregate error in those compared to what the real state was, nobody can give you a better set of states. So, enough with the words, let's take a look at what this really means. So here's our system, that's our robot, we want to give it commands, and then we want to get the state out of it. We'll call the state vector x. I said that could be just whatever we're interested in. It could be the x position, could be the y position, maybe we want the heading theta, maybe we want to know the velocity of the robot, or those different parameters. So that's it, right? We've got our robot, we give it a command, we've got our state. That's what we're after. What else do we need? Well, problem is we can't see that state. That state's hidden. It's the real physical part of the robot. It's the position on the floor, it's the speed. We don't know what that is. We can't access directly the physical state of the system. So what we end up doing is we add sensors and we take measurements. So everybody understands that. There we go, we've got measurements, now we've got measured versions of the state. So, okay, now that's good. We're happy, that's all we wanted to do. We can measure our robot, we can give it commands. We're happy, let's go home. Still not so fast. We mentioned sensors are noisy. So there's noise at the sensor that shows up in the sensor data. We can't probably measure everything we want about our robot. There's only a subset of the states that we're actually going to be able to measure in some way or indirectly. And just to make it harder, obviously the process is noisy too. We tell our robot drive a meter forward, it doesn't always drive a meter forward, right? It hits a bump, it slips, it dives around. So the physics and that part of the system is noisy as well. But I guarantee you that 99% of us who build a robot here, that's what we've built, right? And that's what we've done. We've put sensors, we've taken measurements, and we've tried to do the best we can based on that. With mixed results, we would say usually. So the topic of this talk was improving your robot. How do we do that? We had a Kalman filter into the loop. So we talked about the Kalman filter having a state. So that's just our list of variables. Now they're in the computer, they're numbers in the computer. We have some initial state. We have our model, that's our mathematical equations that simulate our robot. So every time we give the real robot a command, we'll call that U, to drive forward a meter, we send that same command into our model. The model takes what our current state is, that's our current belief in how the robot, what position, where is it in X, Y, Z, what speeds it's going. We feed them into the model does its thing, does its simulation. We feed in Q. Q is an information about the noise. We talked about the model and the system, the real world being noisy. We have to characterize that noise to some degree. So there's this matrix Q that goes into the model, into the algorithm as well, that tells us something about that. But then we run the model and it comes up with a prediction step, which is just an updated version of the state based on the command. And then we do the next step, which we take those measurements. They were now incomplete, whatever measurements we can get. And we also have the matrix R that tells us about the noise that we expect and understand about our sensors. We have to characterize our sensors and how the noise is there. So we're going to feed those into the Kalman filter, and we run an update step. And the update step produces a new state. We said it was iterative, so what we have is the input is now, we've got now an improved estimate of how our robot works, of what it's doing, where it is. So that comes out, and we get mu and sigma, okay? Bet you're expecting we were going to get X out of there, right? No, as I said, the Kalman filter is an estimator. It's going to give you an estimate. We can't ever see the real state. So what mu and sigma are is an approximation of the real state. There's two parameters there. We'll talk a lot about what they are and how we interpret them, what they tell us about the world and our robot. But as I said, it's the best possible algorithm. So if we could measure the difference between our estimate and the real state X, call that the error, no other algorithm is going to give you less error in its estimate of the state than the Kalman filter can. So long as it's linear and using Gaussian noise, all that sort of stuff. So,
is there R, is that a rotation matrix?
No, it's a covariance matrix, which technically is a rotation matrix, but that's it's all of the noise matrix sigma, and we're about to talk about this a lot. The sigma in the state, the Q and the R are all covariance matrix. So there's three areas we have noise that we have to deal with. There's the R, the measurement noise, that's characterized by a measurement covariance matrix. Process or system noise, that tells us how random our real robot in the physical world is. And sigma, that tells us when the answer comes back, it tells us how reliable, how much noise and how much uncertainty there is in that final estimate. So to understand these, we said that they have to be Gaussian to be able to play the rules of using them on a Kalman filter. So we'll talk about what it means to have Gaussian noise. So we're also going to characterize all of this noise in the terms of being a probability. So we're going to talk about noise and the probability of noise. So let's say these were some measurements we took with a sensor. So they're returning a bunch. If we look horizontally, that's distance, the range of the reading. And the height of the little plot would be, I've done a whole bunch of readings. How many times did I get this range? How many times did I get this? So we get a whole bunch centered on, we call it mu, it's the average, the mean. That's probably close to where your real measurement distance is of whatever you're trying to sense. And then we would get some random spread, and we get some noisier, further, greater than or smaller than the measurement we expected. So we can take that and take it to the screen. We can actually plot a graph around that. That graph's called a Gaussian function. So to call it a probability, and now we're going to start interpreting these graphs as probabilities. So what that's telling you is to make it a probability, we have to normalize the equation so that the area under the graph is always 1. 1 represents 100% probability. And we're going to talk a lot about interpreting this. But there's this equation now for the Gaussian. So it looks kind of scary, but we can represent that entire function that gives us all of the probability about our noise source just from this one equation. But if you notice, there's only really two interesting variables in that equation, mu and sigma. Everything else is a constant, except there's x up there on the top. That's my input, what I'm asking about, the position in the graph. And mu and sigma, everything else is a constant. 1 over 2 pi, that's a constant. That's the normalizer that makes us all come out to be 1 when you measure the area under it. E is a constant of half. So there's only two parameters. Sigma we call the standard deviation, and that characterizes how much noise basically is represented. And we have the mean, which is the center where the position of that peak of the measurement is. So the important takeaway here is we drew that graph that represented the entire distribution of the noise in our sensor. But using this formula, we can characterize that noise using just two numbers, standard deviation and mean. So any sort of set of Gaussian random noise, you can calculate what these parameters are for it. Our algorithm, the Kalman filter, doesn't actually, the estimate is not a number. And we have to be very clear on that. The output that it gives you is not what is the position of my robot. We have to do some work to kind of figure that out. The output is these two parameters. For each state variable, you'll get one of these parameters. And it's very important that we'll talk about how do we use them to interpret and get useful data out of the algorithm. So that graph, the curly graph, everybody wants to just measure that and say, well, now if I'm at X and that's the height, that's the probability. To get the probability, we need to do more. So here's just a little bit more showing you how those parameters work. Right? So here's a graph, sigma's 1, it looks like this. Right? If I had sigma 2, I'd get a graph that looked like this. And I realize that we've normalized them so the area under both graphs is both equal to 1. But the one with sigma 2, it's more spread out. If I had that characterizing my noise, it would mean I get more often, I'm getting noisier data. Right? Because out to the side, there's a higher probability, there's more area out to the sides than there are near the middle of the graph. So the important thing is sigma just tells us how noisy effectively our signal is. We can characterize it by, I've just plotted, each graph has this value sigma, the standard deviation. So for the yellow graph, plus or minus 1. For the brown graph, plus or minus 2, because that was its sigma. And I said, to calculate from these graphs what the probability of something is, we need to measure the area within a range under that graph. And just there's some standard values that are common to be within one standard deviation. It doesn't matter what sigma is, but if you stretch it out to one standard deviation, you always get 68%. Right. So if that was a probability of the position of X of my robot being somewhere close to 0, what that would be telling me that there's a probability of 68% that my robot is within plus or minus 1 unit of 0. Right? Because we got the area is bounded by 1, which means plus or minus 1 unit distance from the mean. And we can calculate the area that that graph has with the standard deviation of 1, and it's 68%. If on the other hand I was using this graph, which was telling me about the noise, it's got a standard deviation of 2. So now I have a 68% chance that my robot is actually between plus and minus 2. So there's twice as much noise in there. With the same, within one standard deviation. In this case, it's out to plus or minus 2, with the other graph it was plus or minus 1. So you can see how the width of that area tells us the area I'm interested in. I can never ask the probability of my robot being at, say, exactly minus 1. So you're going to be very disappointed. I think that's one thing I really want to make clear. I think most people who play with these sort of algorithms see this mean and standard deviation and go, I don't know, I'm just going to use the mean. We all know what the average is, right? That's got to be close. So they'll throw away and ignore the standard deviation. You'll say, well, the mean, that's the biggest bit. That's got to be the best thing, right? I'll just use that as my estimate of where my robot is, wherever the mean was. If we take the mean and interpret it as a probability, the probability that your robot is at the mean is going to be very disappointing. It's 0. Right? There is 0 probability that your robot is actually at the mean.
Especially when you demo it.
Yeah, well, we'll get there. So we always have to consider an interval. That's the same with any. If I ask what the probability is, it's at minus 1, it's at 0. Because under a single point, there is 0 area in that graph. It's an infinitely small slice. We have no area. So the probability that your robot is at an exact, precise position, it's always going to tell you 0. So we always need to look at these intervals. So here, again, we look at now what's 2 sigma. I've showing you examples where I measured what was 1 sigma. It's 68% of the probability always is within 1. If I go out to 2 sigma, this graph, the standard deviation is still 1, but I'm saying doubling that when I look at the interval. And now I've got 95% probability that it's between minus 2 and 2. I had 68% that it's between plus or minus 1, because that would match, and I have 95% probability that it's somewhere in the interval between 2 and minus 2. If I say take 3 standard deviation, I'm down to 99% certain. It's pretty obvious, right? The whole graph is covered pretty much by the time you get to 3 standard deviations. So we can say our robot, 99% sure it's between plus or minus 3. We don't have to, standard deviation, they give you, there's 3 numbers that I've just, 68, 95, 99, everybody knows 1, 2 and 3 standard deviations, remember. We can actually ask other questions, still got the same graph, it's still got a sigma of 1, but now I just say, what's this probability that I'm within half a meter? And now it's down to 38%, so you can see I've got 38% probability. If I move the mean, all that does is slides it sideways, the probability doesn't change. Right? So I've got a mean of 5, now my axis, all my numbers shifted, but I still look within that same width interval around the mean, I still get 38%. Same if I move it to 0.8, the same probability happens. Along with that, now we can look at different intervals. I've got an offset mean, I've got a different standard deviation, I've got 52%. 70 or 68%, 27%. Now we don't have to always ask what is it plus or minus something around the mean. I can ask what is the probability that my robot's between 0.1 and 0.5, right? So the mean actually tells me nothing. That mean is just it's the way you set up the graph, and then you have to ask questions of this graph to get probabilities of certain conditions. I always have to ask what is the probability my robot is here, or what is the probability my robot near here. I can never say here, 0, right? But I can always put some bounds around the position and I can get an answer. But I have to do more math to get this than just look at that graph. But the graph is useful because it's characterized by these 2 parameters, mean and standard deviation. And those 2 parameters are what the Kalman filter calculates for us. So I just want to explain that we're going to be interpreting the output. There's a lot of work you need to do to interpret the output of mean and sigma. Don't just ignore it, think it's the mean and go there. We'll show why that's a bad idea later. So that's Gaussian probabilities. Let's take a look at it in working. Here's my robot, it's driving towards the wall. It's using a laser pointer to measure its distance. So we're going to step through and show how a Kalman filter and those steps we talked about earlier, taking the input state, doing a prediction, doing an update, how that affects the probability of where the filter thinks my robot is. So I give it an initial probability, I'm uncertain, so it's kind of a low squishy graph. I could calculate the area, if I wanted to know how close it was to a certain position, I could do the calculation assuming I knew what mean is. Sigma is going to be represented by how fat these graphs are. So I start with some initial probability. My robot's most likely somewhere in that area, right? If I go way out, it's obviously 0. But we run the filter step, we give our robot a command. We take a measurement Z. That's also a probability because it was noisy, right? So we have to treat our measurements as noisy, so they also create Gaussian functions. I then run my prediction step. I run it through the model. So the model's basically taking where is my current estimate of my state. It knows the robot drove forward, so it kind of gets slid forward. But it also got noisier because we told it, well, every time the robot drives, it's a little uncertain, so we don't rely 100%. So you notice that my new estimate there got wider. We actually added more noise into that estimate in the green bit. Now we run the magic update step, and we come up with a new estimate. This is combining now the measurement with the prediction state, and we get this new state, new, and that becomes a new state. You can see already in one step, it's got a lot more accurate on where it thinks that robot is. We started with a pretty squishy, wide probability as our initial state. After just one step, it would have come out and said, this is your new state. So now we rinse and repeat. We send it forward again. Where aren't you going forward?